Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're going to take a look at satellite navigation system. So let's dive right into it. Now first thing you have to understand what the heck it is. Basically if you want to know your location on Earth, that's the requirement, and it should work anywhere on the Earth. It's not like a regional navigation system where you are using radio towers to know your location within a country or within its range. It should work all around the globe. Basically no matter where you are in this, it should work. Now on top of that, it should also work on low power. Now that low power is a critical part because we had satellite communication for a very long time. However, if you have ever seen a satellite phone, they are big, bulky and very power intensive. Like talk time wise, they do not last very long. So this is supposed to be in terms of energy power, very low energy. So this is our requirement. So what you need for in order to create a global positioning system, first you need satellite constellation. This is a critical part. You can't rely on one satellite or few satellites. You need a constellation. You need multiple of them, more the merrier, and they will be having different orbits. Some can be in geostationary, some can be low Earth orbit, some can be in between, and there are many things for it. So that's why we never call it satellite system. It's a constellation because it has many satellites. And you need atomic clocks. It will become more apparent when I talk about principles of it, but think of this, like you need satellite constellation and you need very high quality atomic clocks. Now this is the example of first atomic clock that we had, Nobel Prize grade, and it is a microwave atomic clock. Let's just say it consumes a lot of energy. Of course nowadays we can make atomic clock that is very small and size of a smartphone, like half of a smartphone, and it consumes less power nowadays, but you need atomic clocks. And on top of that you need receiver, obviously, because satellite is not gonna scream at you and it's like, okay, you are here, your receiver should do that calculation. So we need receivers. You must have seen this sort of thing in your old cars or even your mobile phone. So how the heck does this magic work? This is the part where I find all the other YouTube explanations kind of lacking certain parts. Like, of course there might be some good ones, but I haven't found anyone that I can truly rely on. So I will try to give you guys a layman's explanation how the heck the system works. Now this is a layman's explanation. Please do not dissect how the heck it works. It's just a good idea to get you started. First, we assume light speed is constant. Now if you are familiar with light speed, that is 300,000 kilometers per second. We just roll with it, just roll with it. Whatever it is, whatever value we decide, it's constant. It's not gonna change. The speed is constant. Okay, good. Now what does that allow us to do? Simple. Distance is speed multiplied by time. Basically, let's say you know the speed. Let's say you are traveling 100 kilometers per hour. Okay, but somebody tells you you have been traveling for, let's say, 2 hours. How far have you traveled? You have traveled 200 kilometers per hour. That's the whole point. Distance is speed multiplied by time. So I have already classified that speed is locked. It's not going to change. Constant speed, light speed. Boom. So you need time. Now I already said you need atomic clocks for that. Why? Because of light speed. As you can see, light speed is very fast. Basically, if you fired light speed from North Pole to South Pole, let's just say even in less than a second, you will go from point A to point B multiple times. So we need basically something that goes below a second. Basically, you take a second, you stretch it out. You go stretch it out so far that you have now nanoseconds. At nanosecond, light travels only few meters. Now of course there is much more precise mathematics to this, but think of it that way. Like you stretch a second, now you're like, okay, if I count for this 1 nanosecond, light has only traveled, let's say 10 meters or 3 meters, that way. So you just took a second, stretched it. You need very accurate clocks for this. Hence why we need atomic clocks for that, because we need reliably count that second, because second is way too big for us. If you're counting with something that is that fast, you need nanosecond. The more reliably you can count the nanosecond, higher your precision. So that's why you need clocks. Okay, everything fine here. Now how do we do the mathematics? Now that mathematics is has two parts. First part, let's discuss how a single satellite talks to you, not the constellation, the single satellite. So let's say there is a satellite there. How do I know how far that is? All I have is communication and clocks. How do we do that? Well, we apply something known as time of arrival ranging. Think of that way. Let's say you just assume for a second that both of your clock, basically the clock you have versus the clock that is on the satellites, is absolutely synced. So now you can decide a time. Let's say at 12 a.m. The radios on the satellite is gonna broadcast something, whatever it is. It's just gonna say hello, let's just say. Now you know for a fact that your clock is synced. It also knows for a fact that its clock is synced. Now it's gonna broadcast that signal at 12 a.m. You're gonna receive it 12 a.m. plus few nanoseconds because you are not next to it. It took time for that few nanosecond. You will feed into this few nanosecond multiplied by speed of light. That will give you the distance. Now you know your distance. This is what we call time of arrival ranging. Basically, if somebody tells you that your car is traveling 100 kilometers per hour and you have been traveling for, let's say, 10 hours, you have traveled 1000. So it's as simple as that. That's all you're doing. This is what you do with one satellite. Now then the question becomes, okay, all I would know is like how far that satellite is. Doesn't that helps us our solution? Well, not really, because now you know where you are from the satellite, but the satellite is moving. Not to mention, now you only know a circle. Basically, let's say satellite is here, it broadcasts something, there is a circle. That if you take a tether, basically a rope or something, and you stretch it to whatever distance it is, you can trace out a circle. Because you can't be in the center, because the distance will be smaller. You can't be further than that because distance will be longer. So all you know is the distance. So right now you traced a circle where you are on the planet Earth. Now you're like, okay, that's really not that helpful. Of course that's not helpful. That's why we need more satellite. Now let's say you found another satellite, let's say one satellite from here, and it's like you did the same mathematics, time of arrival time of arrival ranging. Now you know, okay, how far that is. Okay, now you have two circles. Now you can do this experiment with yourself. Take 2 coins and try to intersect them with each other. Like just put them on top of each other. You will always find there is only 2 points where they intersect, not overlap, intersect, where they intersect. The lines basically intersecting. You'll only see there is only 2 points where it can intersect. Now that's okay. Now you have narrowed down your field, but still that point could be far apart. Basically, one point could be in India, another point could be in Pakistan. So still not useful. Now imagine you did that with third satellite. Now where can you be? Only at one position, because these 3 circles can only intersect at one. Try that with a coin if you are having hard time. So that's why, like, try drawing 3 circles and making sure they intersect with each other. They will only intersect at one point unless you draw them on top of each other. So because I already told you, satellites are moving and it's a constellation, there's always more satellites and they always are from different angles. And now you figured out your position based on these 3 spheres. This mathematics is what we call trilateration. Be mindful, I am giving you an example of circle, but it's not a circle, it's more like a sphere, because radio waves are like kind of omnidirectional. Even though they are directional like towards Earth, they are like you are drawing a sphere. So based on this sort of mathematics, we figure out your position. What is trilateration? Basically bigger brother of trigonometry. So now you might be considering, how the heck my mobile phone can have synced time with a satellite? That's a very good question. This is the part that I find all the other YouTubers has assumed that but it took me longer time to figure out what the heck is happening. Is that your mobile clock has what we call oscillators. Everything has an oscillator, basically like a wristwatch to a wall clock has oscillator. Now those oscillators are pretty damn good. However, they drift. That's the biggest problem with them. They drift. Like if you let them run, like this clock is running, over a course of a month, it's gonna drift to a 1 second. Over a course of a year, it might drift as much as 1 to 2 minutes. Over the course of a 10-year, you might be off by a whole day. And that's exaggerating, but you can understand that. If you can't rely on this. However, even with this kind of lousy accuracy, the oscillators are very accurate to second. Basically, if all you are doing is like, okay, count to 1 second, 1 second, next second, it will be very accurate. It will be close enough for your mathematics. Basically, we need nanosecond. This oscillators can take care of that. However, because it can start drifting, the moment you start relying on it, it will drift. We reset it. Basically, you receive the signal from a satellite. Now, satellite is gonna say hello. Now it's not gonna say hello, it has a long data point. What is that data? First, I am GPS, because there are multiple concepts. So okay, I am GPS. Your mobile knows, okay, I got the GPS signal. Okay, cool. Now the satellite's gonna say, I am satellite number 12. Let's say this. Now that gives you a rough idea. Now you're like, how the hell now I know where I am roughly on Earth? Because the satellites are moving, and in a constellation, the satellite when it's going, it will tell you if it's let's say 6 p.m. Greenwich Mean Time or whatever its own personal code is. You must be here. You must be either above equator or below equator. You must be from here. You're not knowing exact calculation, but your coordinate wise you got a rough idea like where you are. Now this is not good enough. Unless you are trying to destroy a continent, it's not good enough. So now you have that information. It screams the time. All that it screams is like, I'm gonna scream every second. Now this every second, it could be very low, like it could be screaming 1,000 times per second. So what your mobile does is like, okay, I received a signal, it says it's gonna scream after a second. Basically from its point of view, after a second, it has to wait a second because it's screaming every second. So it's gonna start a stopwatch. It's like, okay, 1 second has passed. Now it resets the stopwatch and starts it again. Now few nanoseconds later it will receive the signal. Now why the heck that there was the delay? Because the satellite was far. I told you the satellite is screaming every second. Your watch that is in your basically mobile, it's basically good enough for 1 second. Now it removes that 1 second from the equation and then gives you few nanoseconds, the delay it took. That few nanosecond goes into this equation, few nanosecond multiplied by the speed of the train. Now you know the distance. Now that time data, you will always hear people say like, GPS is broadcasting time data. It's not broadcasting 6 a.m., 7 p.m. or whatever like that. It's simply saying 1 second, 1 second, 1 second, 1 second, 1 second has passed basically. Now it does that multiple frequencies. Now that frequency is a military guarded secret, so I do not know. So in older days, the frequency was like, you would not be allowed to refresh fast enough and accurately enough. Basically the nanoseconds, they were giving you like, okay, 100 nanoseconds. That makes the basically receiving data very, very vague. So you can only be sure of in 100 meters. Nowadays you can receive up to 10 nanometers, 10 nanoseconds. Now you can be like, okay, I am within this 1 meter square. So that olden days, the problem was GPS is a military system. Military created it, but for aviation industry, they allowed a smaller, basically the signal that is coming out, they decrypted a small amount of signal for that. Using that decrypted signal, you can be like, okay, fairly sure. But an accident happened where a passenger jet that was drifting and relying on GPS, it drifted so far away that it ended up in another country and unfortunately ended up on top of a no-fly zone of a military, and it was shot down. Passengers were killed, like all of them, because a missile versus a jumbo jet, there is no competition there. So after that, US government decided to open the much further into the signal. There is still signal is this long, they only opened this far because the clockwise you are not getting this large data. This is reserved for ICBMs. That's why you can be sure like modern receivers, GPS receivers are much more accurate because they have much more data to work with compared to older days. Older days, best case scenario was 100 meters. They were barely useful for aircrafts, and they were very useful overseas for container ships, but they were not much more useful. Definitely not useful for automated cars. So as military opened the data point up, you can receive much more precise data. Now you can calculate much more precisely, and voila, you get much more precise data. So even if it's this precise and nanoseconds we are talking about, you should be within 1 meter. Why the heck you are never that accurate? If you are familiar with the GPS and you must be using it, you must have noticed many times you are driving a car on a road in a lane and it shows you driving parallel to a road because it's drifted. How the heck that drifted happened? That fudge factor. Now that fudge factor happens because nothing is constant in this universe. Light speed changes because you are coming closer to a gravity well of this planet. It changed because the satellite is moving. That changed. Doppler shift, everything happened. Now of course they are changing very little. It's not like a big difference, but that little bit adds up. So after that a while, your accuracy, even though on paper it should be like you should be within this square foot, it becomes the square meter, like basically 3 times. That fudge factor comes from the fact that light speed itself is not absolute constant. Then even the clocks on the satellite, they are very damn good. The clocks or the oscillators in your mobile phone, they are not that good. So you always have fudge factor because of your own receiver. The receiver might be off by like 1 nanosecond or 2 nanoseconds. So there is always a fudge factor from your end. Not to mention on top of that, because we knew from day one that 3 satellite, even though mathematically good enough, it is never practically good enough. So we always rely on 4 satellites. Your receiver will never give you an absolute signal unless it has 4, because 3 you may still have a bit of fudge factor, but 4 will always have a reduced your margin of error. If you have 5 or 8 or 15, you're golden. Now you might be like, how the heck that will happen? We rely on multiple constellation to do that. So GPS, when it was built, it was the first system, so many things were being figured out. So they knew from day one 3 is simply not going to get it, and they wanted 5, but they realized they need more satellites for that, and they only had budget of few, so 20-ish satellites. So we don't have enough satellites. That gives a very big margin of error. Then on top of that, GPS is built for this ICBMs. Because of this military encryption, you do not get the full data that satellite is screaming. Satellite is not going to judge you. Satellite is not going to say, oh, this mobile phone, I'm going to block it. Satellite is screaming. It doesn't have enough energy to go find every mobile receiver that's receiving it. Simply it screams the data, and military is responsible for coding and encoding it. So they encrypt the data. Now that encrypted data also contains what we classify as altitude data, basically how high you are. Now you might be like, wait a minute, I thought GPS doesn't have the high data. It does, because the mathematics that we are doing is inherently 3-dimensional. Think of it this way: Earth is a sphere. So how the heck do you know where you are? Because if you think of Earth is in a flat surface, yeah, it makes sense. You only have 2-dimensional data, but Earth is a sphere. So you need the third dimension. Otherwise, you will not be able to pinpoint where you are. That data is limited. You cannot access it. Military satellites, military missiles, they can access it. That military access, that's how they were able to, without changing the satellite, they were allowed allow us to receive the signal, because they can simply change the encryption or unlock it. So what can we expect in the future? Now first, Constellation, I already told you, because USA, when they built it, it was a military system. They had a military budget limit. So Russia comes along, it's like, okay, they sees the project of GPS and its success, and they're like, okay, this is the thing what you did nice, but these things you did stupid, so I'm going to improve on it. So GLONASS comes after GPS, and they improve a lot on things. There is old saying in engineering, you do it first or you do it better. GLONASS comes, and because it has learned from mistakes of America, they do it better system. So they put much more satellite, much better basically atomic clock, much better signal strength, and because of their orbit mechanics, if you are on a pole, basically North Pole or South Pole, you have to rely on this GPS, and those poles are not that accurate. These puppies are very accurate there. Then on top of that, comes basically European Union, and they're like, okay, we also want our own system. They established a system which we call Galileo. It's now even better than this. Then China also comes along, and they create their own Bandhu navigation system. Now these two puppies are still under construction. Now they are active, you can receive the signals from them, but satellite count is low. This puppy is full. This puppy is still need basically more satellites basically. So after a while, once we have better clocks, our fudge factor will be reduced. Now it will never be eliminated, but it will be reduced. So at that point, you will be able to reliably count, oh, I'm on this lane of the road, I'm not gonna be on the other lane. This is necessary for self-driving cars. And after a while, because automated drone delivery is supposed to be becoming the next thing in the future, we need altitude data. It's there, the mathematics is already there, the signal is already there. They have to just decrypt it. They're like, okay, remove the encryption. So these are the things that we can accept in the future. Right now, you can buy a phone from MI or some other Lenovo or Motorola that have encryption chipset that can receive GLONASS, Windows, Galileo, GPS. And it's surprising how much quickly it acquires signal, where you are. It's like you take out your phone, start the GPS, boom, where you are. I am old enough that I used very early stages of GPS, and it used to take time. Yeah, now it has detected it, and used to consume a lot of battery. Because now we have so many signal strengths, and multiple satellites. Because I told you, everyone who is building afterwards, they are building it better. So we have much better system and much more interesting satellite systems to look in the future. So this was my presentation on GPS. I hope you liked it or learned from it. In that case, please leave a like. If you didn't, don't worry about it. You can dislike it. I would urge you to leave a comment, and please subscribe, press the bell icon if you're free, and as always, thanks for watching.